Okay, so let's continue our discussion on bounded sets, right? This was what we were discussing, and I'll obviously refer to the previous lecture in order to just recall what we have already done. So in this lecture we start by characterizing boundedness in terms of sequences. Okay, so theorem, what are we intended to do is to characterize bounded sets in terms of sequences. And if you recall quickly, then this is something which we discussed in the previous lecture, that the bounded sets have a prior definition which we have already given, and metrics in case of metric spaces there is also something called boundedness. But when we talk about bounded sets, we refer to the usual definition of boundedness in a topological vector space and not the metric boundedness. Okay, so do not get confused, and that is the thing which I wanted to emphasize at this point. So the theorem is as follows, that let E in X, let E be a subset of X where X is a topological vector space, then the following are equivalent. So what we say is that E is bounded is equivalent to saying that if I have a sequence xn in E, so xn is a sequence in E, and we have a sequence of scalars, so alpha n is a sequence, this is a sequence of scalars, fine, with the additional condition that alpha n converges to 0 as n tends to infinity. Now I won't often refer to n tends to infinity. Whenever I talk about convergent of sequences, it is obvious that we are talking when n tends to infinity. Whatever, what we claim is that then alpha n x n tends to 0 as well. Fine. Let's give a proof of this, and the proof is fairly simple and straightforward. Okay. So now this is a procedure which we are following since a long time, that whenever we are talking about convergence of sequences or boundedness, we are always preferring to choose balanced sets, balanced neighborhoods of the origin, right? And that is some sort of a procedure which we will be eventually following, because a balanced set is of much use, right? You can just scale it using scalars whose distance from origin is less than 1, and it will be still the very set you started with, right? Whatever, suppose E is bounded, let V be a balanced neighborhood of the origin in X, then E would be contained in TV for sufficiently large T, right, by boundedness, for sufficiently, wait a minute, for sufficiently large T, right? This follows from the usual definition. Now let xn be a sequence, fine, and I have a sequence which converges to 0, right? And alpha n is a sequence of scalars converging to 0, But what do we essentially mean by converging to 0? So by converging to 0 means it's eventually in every neighborhood of 0 in some sense, right? So if I apply the definition in a bit twisted way, so if it's converging to 0, then there exists some natural number n, and in fact you don't even emphasize what the indexing set is. You can just consider this to be more generally to be a net as well, but that won't differ any problem. So there exists some n such that mod of alpha n t is less than 1. Fine. Fine. And this happens if n is greater than a. Right. This follows from the usual definition of convergence, right? You know, I can approximate the value 1 by t by an epsilon greater than 0. Right. This comes from this is straightforward from the usual epsilon delta definition of convergence. Whatever. Now, since E is contained in TV, now so therefore T inverse E is contained in V. But once T inverse E is contained in V, so what can we have directly from here is that alpha n x n, this is also in V, right? Why is it so? Since V is balanced, right? And this happens for all n greater than a. But V was an arbitrarily chosen neighborhood, right? So this implies that alpha n x n converges to 0. Fine. Okay. Okay. Yeah. Conversely, what we would have, conversely, suppose E is not bounded. Suppose E is not bounded, so then there exists some neighborhood V of the origin such that, you know, there is a sequence of scalars which when used to scale V is never contained inside, right? That is negating the definition of boundedness in some sense, and there exists a sequence of scalars Rn such that Rn converges to infinity and no Rnv contains E and no Rnv contains E. Fine. So using the same index as n, I mean as Rn, I can choose a sequence xn from each of these Rnvs, right? So choose xn in E such that xn is not in Rnv. Fine. But if xn is not in Rnv, then that implies that Rn inverse xn is not in V, right? But so V is a neighborhood of the origin, it is an arbitrary neighborhood of the origin, or at least it is some neighborhood of the origin, and we have got a term of the sequence Rn inverse xn which is not inside V for any n. That means this sequence Rn xn cannot converge to 0. This implies the sequence Rn xn, Rn inverse xn, sorry, it does not converge to 0. So this is some sort. So you can take the contrapositive, or you can in fact, you know, go for a contradiction. This contradicts B. Why does it contradict B? Because we have chosen the sequence Rn such that Rn tends to infinity. So Rn inverse, this sequence will tend to 0. So it immediately contradicts B, right? So this contradicts the second statement. I don't remember how I had serial that. So this contradicts B, or at least the second statement. Fine. Okay. Now let's introduce the notion of a bounded linear transformation. Okay. So the definition which we would be applying here for a bounded linear transformation, which will be slightly different from what we have usually read as a bounded linear transformation. Okay, let us first give the definition and then we will talk about it. So let x and y be topological vector spaces and lambda be a linear function. So x to y be a linear map, okay, or a linear transformation. Then gamma is said to be bounded, sorry, lambda is said to be bounded if lambda maps bounded sets to bounded sets. Lambda maps bounded sets to bounded sets. Now in the previous lecture we have read that a subspace can never be bounded, and if it is bounded if it's if and only if it's 0, right? It's the trivial space. So this immediately applies here in some sense, that why can't the usual definition of bounded linear transformations be applied? So let me just state it like this, that the usual definition of bounded linear transformations can't be applied. Why is it so? As if so, then by the usual definition the range of this is bounded, but the range forms a subspace, if you recall. But this is a subspace. In this case it's a subspace of Y, but a subspace is bounded if and only if it's 0. But that implies that R of lambda is 0. But that means that lambda maps every element to the 0 element, or in some sense it's identically the 0 linear transformation. But that's something which is of least use, right? No information we can gather about topological vector spaces if we straight away consider 0 transformation. So, and that's the reason why it's of no use. So we come up with this different definition, and we straight away come to a theorem which sort of gives us a lot of information about these bounded linear transformations. So suppose x, y are topological vector spaces, and lambda is a linear transformation. Then we would say that 1 implies 2 implies 3, and if I will be writing these statements, and if the if x is metrizable, then 3 would immediately imply 4, and 4 will in fact imply 1, and hence if x is metrizable, hence the following will be equivalent. So let me give the statements. The statements are fairly straightforward. First is gamma is continuous, lambda is continuous. I always get confused between how to pronounce whatever. Lambda is bounded if xn converges to 0, then this implies that the sequence this such that n tends to n is in n is bounded. Number 4, xn converges to 0 implies lambda xn also converges to 0. Fine. So let's prove them one by one, and the proofs are fairly simple again. So proof, let lambda be continuous. So I need to show that lambda is bounded. So I need to show that it maps bounded sets to bounded sets. So let E in X be bounded. Fine. Now let W be a neighborhood of the origin in Y. Since gamma is continuous, there is a usual definition of continuity. There exists a neighborhood V of the origin in X such that the image of V is contained in W. Right? Right. Now it's very easy from here. Now since E is bounded, E is contained in TV for sufficiently large T, but then this implies that if I apply lambda on E, then this should be contained in lambda of TV, but this by continuity is just this, or rather by linearity it's just this, and then lambda of V was contained in W, so this must be contained in TW, and this happens for sufficiently large T as usual, which means that this is bounded. Fine. Right. Okay, so we have proved that 1 implies 2 and 2 implies 3 is again very trivial. 2 implies 3 is trivial, it's trivial. Why is it trivial? As convergence sequences are bounded, right? Bounded, right? So if convergence sequences are bounded, so I can choose the set which contains of all these elements, then that set is a bounded set. So if I take the image of that set, then the image will be a bounded set, as we just see, because I have assumed that lambda is continuous while proving 2 implies 3. Fine. So now what we are what we require to prove is that, so we claim this assumption. So now let X be metrizable, and we show that 3 implies 4, and 3 implies 4, and 4 implies 1. So it will make all these statements equivalent. Okay, so let's prove it. Okay, wait a minute. Okay, so yeah, so now we are intended to show that 3 implies 2. That is, if xn is a convergence sequence converging to 0, assuming that when xn converges to 0, the set lambda applied to xn is bounded. To show that xn converges to 0 implies lambda xn is converging to 0. Fine. So let's prove it. So suppose lambda satisfies 3. Fine. So let xn converge to 0. Then recall, this was, I guess, a theorem which we have studied while we were studying Cauchy sequences in the lecture on metrizability. Then recall that there exists a sequence lambda n which converges to infinity of scalars such that lambda n xn converges to 0. Then this implies that the set lambda applied on gamma n xn is bounded. Why is it bounded? By 3, right? Therefore, by the theorem we proved just before starting this theorem, but just before starting the notion of bounded linear transformations, what can I say about lambda xn? So lambda xn is lambda in inverse of lambda of gamma n xn. Now gamma n is a sequence which converges to 0. So gamma n inverse is a sequence which converges to, sorry, gamma n is a sequence which converges to infinity. So gamma n inverse is a sequence which converges to 0, and this is a bounded this is a bounded set. So by that theorem, immediately I can say that this converges to 0 as n tends to infinity. Okay, fine. So now we are left to show that if 4 holds, then 1 holds. So what we prove is that if 1 fails, 4 fails. So then we can apply the contra positivity. Fine. How do we do that? So I need to start with the assumption that lambda is not continuous, and I need to show that there can exist. So we will come out with a sequence which converges to 0, but its image does not converge to 0. So let's see. So let lambda be not continuous. Then there exists a neighborhood W of the origin in Y such that lambda inverse of W contains no neighborhood contains. So this is again negating the definition of continuity, contains no neighborhood of the origin in X. But if X has a countable local base, assuming the metrizability, countable local base, therefore there exists a sequence. So you can choose elements from each of these local bases to form a sequence in some sense. By indexing using these local bases, we will get a countable index, obviously. Then there is a sequence xn in X, such that xn converges to 0. But since lambda inverse w contains no neighborhood, so lambda applied on xn, this won't be in any neighborhood of the origin, so this won't converge to 0, or rather this won't be in w itself, which would imply that lambda xn does not converge to 0, which fails 4. Yeah, 4. Fine. So that's the end of this lecture. In the next lecture, we will be start talking about semi-norms and convexity. So meet you guys in the next lecture.